Hey everyone, and welcome to an explainer that is honestly going to fundamentally change how you look at the physical space around you. Today, we're going on this really fascinating journey. We're going to zoom all the way into a single microscopic algebraic variable and then pull all the way back out to massive physical monuments. We're talking about the base scale. It's this brilliant mathematical normalization that actually surfaces complex math and turns it into a totally practical tool for regenerative architecture. So, if you've ever wondered how abstract numbers actually translate into the physical buildings we live and work in every day, well, you're in the exact right place.
But before we really get into the nuts and bolts of the geometry, I want you to consider a pretty provocative question. What if a single mathematical slider could shape an entire city? Literally just imagine possessing a tool where a tiny adjustment to one single number on your screen could seamlessly and flawlessly ripple out to redesign the footprint, the courtyards, and the very structural decay of a sprawling urban center. And doing all of that without losing a single byte of data. I know it sounds a lot like science fiction, right? But the immense, real-world stakes of the geometry we're about to explore make this an absolute reality.
Okay, let's dive into this, because this stunning 3D architectural endgame is exactly what happens when that abstract math anchors itself in a visceral physical space. What you're seeing here isn't just a pretty spiral. It is a full-blown piece of regenerative, monumental architecture. It's built on a mathematical foundation that allows form and function to just perfectly align. We're looking at a structure that's mathematically interrelated, organic, and totally gapless. But to really grasp how we can build something this beautifully complex, we kind of have to understand the historical problem that architects have been wrestling with for centuries. See, for a long time, architects and designers were stuck with this old, incredibly clunky problem. When they were trying to code discrete, overlapping fractals and recursive shapes, they basically had to rely on the Pythagorean theorem. That meant balancing three interdependent variables, A, B, and C. If you wanted to change the size or the decay of, say, a nested room or a structural column, you had to juggle three shifting sides of a triangle all at once. It was computationally heavy and, quite frankly, just mathematically frustrating. The solution to all this? A breathtakingly elegant shift from three chaotic variables down to a unified, single, independent variable, B. Here's the mathematical breakthrough that literally changes everything, and it all comes down to the number 1. By simply normalizing the base of our triangle so that A equals 1, all that wildly complex calculus and vector math instantly surfaces into perfect clarity. When we set that baseline to a constant of 1, the entire base scale framework just collapses down into something profoundly manageable. We no longer have to track a constantly moving target. Instead, we have this rock-solid, unwavering foundation. And that normalization, it gives us this incredibly powerful equation. D equals the square root of 1 plus b squared minus b. It is the ultimate zero-loss parametric tool. Think of the b in this equation as a magic slider. An architect can sit at their computer and literally just push that b variable back and forth. And as they do, it smoothly and dynamically morphs the building's spatial decay rate, which is our d. There's absolutely zero information loss, no gaps anywhere. The math scales infinitely and cleanly, dictating exactly how much a structure shrinks or grows as it spirals inward or outward. Now, what's really interesting here is how this single formula beautifully unifies classical architectural proportions while at the same time totally freeing modern designers. Historically, architects were kind of trapped making these discrete, rigid, structural jumps. You were either using the silver ratio, which is what you get when you set our slider B to 1, or you were using the golden ratio by setting B to 0.5. But with this normalized equation, you aren't locked into those ancient fixed presets anymore. You can smoothly sweep B anywhere from 0.1 to 0.9 for total custom microtuning. You can dial in the exact spatial decay rate to perfectly fit the acoustic, physical, or structural demands of a specific building site, all without ever breaking the underlying geometry. Let's look at the visual proof of this in action. We're going to skip the dense jargon here and just show you what happens when you sweep that variable. You get this base scale nesting pattern. It basically creates a squared spiral of gapless, overlapping rectangles. Notice how perfectly every single block fits into the next one, like a giant puzzle? That is zero-loss modular tessellation right there. The math practically guarantees that no matter what your decay rate is, the physical boundaries of your structure are always going to lock together seamlessly. And this actually brings us to a massive shift in how we plot physical space. Unlike traditional linear perspective, which, always relies on a global point of origin and a vanishing point way off in the distance, this geometry is rotation invariant. It creates these continuous recursive loops. The base scale operates as a symmetric forward-focused map. It's got this totally intuitive I follow my feet directionality to it. You don't need a vanishing point because the geometry is just endlessly nesting within its own finite boundary. It is an entirely new way to think way beyond standard Euclidean postulates using perspective drawing.
So from a practical standpoint, for the people who are actually drawing these buildings in CAD environments like Rhino or Grasshopper, this workflow is an absolute dream. Step 1, you set your offset variable b. Step 2, the system instantly calculates your decay rate d. And step 3, it outputs your finite footprint boundary d. Because of this single variable normalization, the coordinate step size of each nested room scales exactly by predictable powers. It makes writing the code for modular tessellations incredibly lightweight and highly efficient. You can literally model a whole modular city under a unified coordinate space without your computer crashing.
So the crucial point is this specific boundary equation right here. When we integrate our normalized math with the number of nested loops, which is represented here by n, we can solve for the exact central courtyard or atrium area of a building, which is D. Let's say you want a building that spirals inward 4 times, and you want to ensure exactly 25% of the footprint is left totally open as a central plaza. You can solve for B directly. This exact formula gives construction teams the precise mathematical coordinates they need to physically tape out that plaza on the construction site. Zero guesswork. It saves massive amounts of time and budget. And this brilliantly illustrates one of the most mind-bending aspects of this entire geometry. It's completely scale agnostic. The exact same line of math that designs a pocket-sized, intricately crafted silver pendant flawlessly structures a massive concrete town center. Because this mathematical foundation relies on a scalable, zero-loss parametric variable, the math honestly doesn't care how big the canvas is. The underlying regenerative electromagnetic pattern holds true no matter what. And guys, this isn't just theory. This is happening right now in the real world. There are active architect competitions utilizing this exact math to build regenerative structures today. We're talking about actually constructing a town center monument at the Meta campus in Costa Rica, and another one at the Ecovia San Mateo. There are artisan prototypes, inspirational videos, and Metacamp plans being developed right now that leverage this geometric breakthrough. By tapping into this regenerative electromagnetic space design, architects are channeling a totally new form of interrelated, organic movement into the very places humans gather and live. We've traveled a long way today, from a single microscopic algebraic tweak, literally just setting A to 1, all the way to the construction of massive regenerative town centers in Costa Rica. We've seen how surfacing the math behind a simple slider can output a zero-loss, scalable foundation for the future of architecture. So I'm going to leave you, the focused learner, with this thought to ponder. If you possess this exact mathematical key to interrelated organic movement, what would you build with it? Thank you so much for exploring the base scale with me today. And as always, keep questioning the geometry of the world around you.